In today's video, I'm going to continue solving question number 20C, problems 2.3 from elementary number theory by D.M. Burton. If GCD of A and B is 1, then we have to show that GCD of AC and B is equal to GCD of C and B. We assume that D is the GCD of C and B. So we have to show that D is also the GCD of AC and B. For showing that, we will be using theorem 2.6, which says that if A and B are any non-zero integers, then D is the GCD of A and B if, number 1, D divides A, D divides B. Number 2, whenever C divides A, C divides B, then C divides D. Okay? So let us show that D divides AC and D divides B. From here, if D is the GCD of C and B, it implies that D divides both C and B. Now D divides C implies that C is equal to D times N for some N. From here I can multiply by A on both sides in this way. Implies that AC is equal to D AN, which implies that D divides AC. Okay, so D divides B, D divides AC. So the first one is done. Next, we will be showing for the second one. Okay, here we won't use any letter C because C is already there. We will choose another letter, say K. Okay, this is the first one. Now the second one. Suppose K divides AC, K divides B. Then we will be showing that K divides D. Okay, how to show that K divides D? We should show that D is equal to K times something. And for showing this, we will be using this one and this. So let's see. Now, D is the GCD of C and B. So it implies that D is written as a linear combination of C and B for some X and Y. For some X and Y. From here, K divides B. K divides B. So it implies that B is equal to K times M for some M. For some M. Okay. Then this equation 1 implies D is equal to Cx plus Km Y. Okay. Now we are near to the proof. See, we already have K here. If we can show that C is a multiple of K, then we can take common and conclude that K divides C. So let's see how to write C as a multiple of K. We use this one. Also here we have GCD of A and B is 1. So it implies that 1 is written as a linear combination of A and B for some U and V. For some U and V. Okay, now I can multiply on both sides by C. The reason that I'm multiplying by C is because I want to make use of this. But K divides AC. So it implies that AC is equal to K times R for some R, okay? For some R. So therefore, what would be your C? In place of AC, I have KR. So KRU plus, what about B? B is KM. KM CV. Okay, so here we have K RU plus MCV. Then this one, okay, equation 2 would imply, in place of C, what do I have? This one, K times RU plus MCV X plus K MY. Now I have K RU plus MCV X plus MY. Clearly from here we conclude that K divides D. Okay, so the second one is also done. So therefore D is also the GCD of what? A, C and B. Thus GCD of A, C and B is equal to GCD of C and B. Let's do the next one. If GCD of A and B is 1, then GCD of A square and B square is 1. For showing this, we will be using the previous one. That is GCD AB is 1, then GCD AC and B equal to GCD of B and C. Okay, so let's see. Now in place of C, I will put A. So if I put C to be A, then therefore GCD of A and B equal to 1. We have here GCD of, in place of C we have A, and this is equal to GCD of A and B, which is equal to 1. I'm using the previous one. A square comma B equal to GCD of A and B is 1. Also GCD of A and B is the same as GCD of B and A, so I apply the previous one, which is GCD of B square comma A equal to GCD of B and A, which is equal to 1. Okay, so from here we see that from 1 and 2 we see that GCD of A square and B is the same as GCD of B square and A. Now again I apply the previous question to this one. Again apply the previous one. Okay, apply that question 20C. We have GCD of A times A comma B equal to GCD of A comma B square equal to 1. So it implies that, or therefore we conclude that GCD A square comma B square is 1. Okay, hence proved.